Hi, and welcome to 15.6 Critical Angle and Total Internal Reflection. Total internal reflection is a special case of refraction. So we're still going to be doing Snell's law. We're still going to be having these diagrams that look like this with the different medium interfaces with the rays and the incident angle and the refracted angle. But the difference is it's a very weird case of refraction. So this is a PhET simulation of a laser that is currently in air and it's going into water, the classic example, and you could see part of it gets reflected and part of it gets refracted and bends as it enters the water. By the way, if you make the incident angle, is this incident angle 0 degrees or 90 degrees? Well, it looks like there's a 90-degree angle there somewhere, but remember the incident angle is measured with respect to the normal. So what is this? It's approaching 0 degrees with respect to the normal. So if the light is just going straight through the interface, no bending occurs, but it still slows down. And if I change it from a ray to a wave, hopefully you could see without too much of the, the loading happening, the buffering. Well, it's supposed to slow down as it enters the water. And it's kind of cool. You go like this, and you could kind of see why it bends is because remember, it's a wave. So as part of the wave hits the water, it slows down, but the rest of the wavefront is still moving fast. So that leads to that bending idea. Well, we've seen this before. Let's talk about why total internal reflection is different. As you could see, as the light enters a more optically dense medium, it bends towards the normal. And if we change it, so now it's going straight through because it's the same. If we change, oh, whoa, that's kind of a spoiler alert. All right, if we change it like this, you could hopefully see that it bends away from the normal. And if we even change this, let's make it all the way. Okay. So now you could hopefully see that it's definitely bending away from the normal as it enters the air on the bottom. So it's bending away from the normal. Well, what if we increase the incident angle? What if we increase it more? You could see it's bending away from the normal. Well, what happens if it bends and now what's that refracted angle there? I'm trying to get it so it travels along the medium interface. And if it's going right along the medium interface, what's the angle of refraction? Between the normal line and the medium interface, that's a 90-degree angle. So theta r in the Snell's law equation, theta r, theta 2 is going to be 90 degrees. That's the critical angle. So actually the incident angle here between the normal and the incident ray, all right, that is the critical angle when the angle of refraction is 90 degrees. And if you go past the critical angle, you get this phenomenon called total internal reflection. And there's a lot of different applications, including fiber optics. So you could use optical wire, which is almost like glass wire, and lasers to transfer data at the speed of light, because the light it stays inside of the wire due to total internal reflection. And the data travels at the speed of light because you're using a laser. So it's really cool stuff. And it all happens because of refraction. So let's do so just to recap really quickly, the critical angle is the angle of incidence that creates an angle of refraction that is equal to 90 degrees. That's the critical angle. If the angle of incidence is greater than the critical angle, you get total internal reflection. If the angle of incidence is less than the critical angle, then you're not going to get that total internal reflection. You get some partial reflection, but part of it is also refracted. So you want that to happen. Okay, so let's do some problems. So number 1 says a ray of monochromatic light is traveling in flint glass. The ray strikes the flint glass air interface at an angle of incidence that's greater than the critical angle for the flint glass. Which diagram best represents the path of this light ray? It's kind of just, you have to know what the critical angle is. And as we just said, if the angle of incidence, that's this, is greater than the critical angle, then you're going to get total internal reflection. If it's greater than the critical angle. If it's equal to the critical angle, it's going to look like choice D. So this is showing the critical angle. You could call it theta C for critical, because this angle, theta R, is a 90-degree angle. The critical angle is the angle of incidence that makes the refracted angle 90 degrees. And if it's greater than the critical angle, like it says it's an angle of incidence greater than the critical angle. If this increases, then this is going to start going this way, as we saw in that PhET simulation. Okay, so that's kind of cool. That's the idea. That's why we started with this one. You have to know what that is before you do the rest. Number 2, I kind of mentioned in the PhET simulation as well. It says, as shown in the diagram below, a beam of light can pass through the length of a curved glass fiber. This phenomenon is possible due to the effect of internal reflection. The light's coming in and then reflect. All right, and then the light comes out here. So kind of cool. You could transfer data by turning the beam of light on and off to transfer data at the speed of light. Number 3, in the diagram below, a monochromatic light ray is passing from medium A into medium B. The angle of incidence is varied by moving the light source S. When angle theta becomes the critical angle, the angle of refraction, do you guys remember? If this is theta C, then the angle of refraction is 90 degrees. That's the critical angle. That's this situation here. That's showing the angle of refraction being 90 degrees. If it's equal to the critical angle, the angle of refraction is 90 degrees. That leads into number 4. Number 4 says, the diagram below represents a light ray traveling from crown glass into air. At this point, I look in my reference table for crown glass and air. So obviously air is right here. We know the N is equal to 1. Crown glass, or glass comma crown, is 1.52. So let's write that in the diagram. So N is equal to 1, and we said this N is equal to 1.52. Now, which one is N1 and which one is N2? In a lot of the examples, the ones on top is normally N1. But if you look at it's not really what's on top, what's on bottom. It's what direction is the ray traveling, or where does the ray start? It starts in the crown glass and it goes into the air. So it's starting here. This is the first medium, N1, the crown glass is 1.52. And then the second medium it goes into is air. Okay. Then, okay, so good. We labeled N1 and N2. Second sentence. The position of the light source is changed to vary the angle. Is this the incident angle or the refracted angle? This is the angle of incidence, or theta 1 for Snell's law, because we're going to do the Snell's law equation. It says calculate the critical angle of the air crown glass interface. So this is a little bit confusing because they want the critical angle, and the critical angle doesn't look like this. You're not going to have it going through the medium like that. You want the angle of incidence that creates the angle of refraction, this theta r, to be 90 degrees. So the diagram is a little misleading because they're showing an angle that's not the critical angle. The critical angle should be somewhere larger than what's shown. So they're saying move the light source over here, and then that's going to be the critical angle. Okay, because you made the angle of incidence bigger so that you get an angle of refraction that's equal to 90 degrees. Okay, by the way, now we're ready to do the Snell's law equation because we have 1, 2, 3 pieces of information, And we're actually solving for the angle of incidence. That is the critical angle that makes the angle of refraction 90 degrees. It's a little confusing because physics is sometimes confusing, but that's okay. So we'll write Snell's law, n1 sine theta 1 is equal to n2 sine theta 2. And 1, don't get confused. And even this is number 1. So you might think, oh, it's definitely n1. No, it starts in crown glass. That's the first medium that it's in. So you got to do 1.52 sine theta 1. If you want to be fancy, you could call it theta c for critical angle. But I'm not really feeling that fancy today. So I'm just going to do like that. And then n2 is equal to 1, because that's air, the index of refraction for air. What is sine theta 2? This is the trickiest part. Okay? We want the angle of incidence that creates an angle of refraction that's equal to 90 degrees. So we need theta r to be 90 degrees in order to find what this critical angle is. And that's the setup. The rest you could probably do because you did it in what is it, 15.4 refraction. But let's do it out anyway. So 1 times sine 90, that's equal to 1. So 1 is equal to 1.52 times sine theta. So sine theta is equal to 1 divided by 1.52, which is about 0.658 when you round it. But don't round it, like leave the decimal long in your calculator, and we're going to do the inverse sine of both sides. So sine to the -1 of your answer. Second sine, second answer is what you type in your calculator. And you get a critical angle of about 41.14 degrees when you round it. So anything greater than that, you'll get total internal reflection. If it's equal to that, you'll get an angle of refraction that's equal to 90 degrees. And if it's less than that, it'll look like what the diagram shows, where there is some refraction happening. And that is it for this homework.